in all actuality, the stuff we're seeing today is not in our textbook. Our textbook jumps directly to 3 variable systems of equations. Today we're going to be talking about 2 variable system of equations. Our textbook doesn't talk about 2 variable systems because 2 variable systems is supposed to be something that you hit really hard in algebra, which you did. Don't get me wrong. But if you don't remember how to do it, it's really hard to do 3 variable systems. So we got to make sure we're solid on this before we get into our 3 variables. First off, does anyone remember what a system of equations is in the first place? I can't. Oh, nope. Doesn't have to do with exponents, or it's not PEMDAS. That's what you said. Nope, that's just simplifying. What's it mean if you have a system of something instead of just an item? I have a machine versus I have a system of machines. What's the difference? They work together. There is specifically more than one that work together. Systems of equations, same idea. I can have an equation or I can have a system of equations. A system of equations is when you have 2 or more. We're going to be working with 2 equations, specifically in the same variables. In which the solution to said equation must satisfy all of the equations. So in which the solution satisfies all. Of the equations. So, not one question, 2 or not one equation, 2 or more equations. Specifically, again, we're going to be focusing on 2 today. We focus in on 2 equations when we're working with 2 variables because the only way you can solve an equation is if the number of variables in said equation matches at minimum the number of equations given. If you want to solve a single equation, it better only have 1 variable. If you want to solve 2 variables, you have to have at minimum 2 equations. On Wednesday, we're going to be getting into 3 variable systems of equations, which are going to have 3 equations involved in them. Now, let's talk about that solution. If you are solving an equation that has 2 variables, that means there is 2 numbers associated with your answer. Not just an x equals, but an x and a y. And generally speaking, when you have an x and a y as a number, it's given to you as a coordinate point. The exception to that rule, when it is not a coordinate point, is situations where the systems of equations don't really work out to give us a singular x or a singular y. Now, you've had this happen before when it comes to having a single equation, and you can have it happen when you've got multiple equations. If it doesn't give us a singular number, then your answer is going to be some sort of a phrase. That phrase is going to vary depending upon the situation. We'll talk about that, and it's going to be phrases that you're familiar with. or at least a version of them you're familiar with. When you talk about the solution to a system of equations as well, though, generally speaking, if the answer has to satisfy both equations, and if both equations have x's and y's, in other words, they're linear, if both equations are linear, then they can be graphed to create a line. Let's try a marker that works. That's better. And if one equation makes that line and the other equation makes that line, what coordinate point works on both lines? The one where they intersect. So, the solution to a system of equations is the graph's intersection. Now, when you're working with systems of linear equations, you got a couple of different possible outcomes on what that will look like. Specifically, there's 3 different possible setups. I'm just going to draw 3 little coordinate grids, nothing too special. For our 3 different setups. Okay, so with our possible outcomes, the first setup is you're going to get something showing up, well, similar to what I already drew on the board. And your graphs don't have to perfectly match mine for this setup. It's just trying to give us an idea of what's going on. The first option is the most generic option, and it's the one that people think of most. Where you got 2 graphs, they intersect at one point. That point right there, that is the solution. When this happens, specifically, it's said that we have one solution. And for a linear equation, that's generally what you want. The other possible setups, though. Because you can have graphs that look like this. How do you describe those 2 lines? Parallel. When the lines are parallel, do you notice they don't intersect? And if they don't intersect, and the intersection point has to be where they intersect, that means there is no solution. The third option that sometimes comes up, and this one you got to be careful. There's my first line. Okay, everyone paying attention? Because you got to see me draw the second one, otherwise you might miss it. Where did I draw it? On top of the other one. 2 different equations were given for one line. Where do those 2 lines intersect? Everywhere. Infinitely many solutions. Specifically, those solutions are every single coordinate point that satisfies either equation because they're technically the same equation. Now, one of the things you're going to eventually be looking at with these is eventually we're going to be doing these without a graph. Today we're going to talk about doing it with a graph and without a graph. Without having a graph, how can you tell if lines are parallel?
They have the same slope.
That's the key thing. They have the same slope. But there's one other key that is necessary for that. Because in all actuality, if these two equations are the same line, won't they also have the same slope? So both of these situations will have the same slope. If you have the same slope, you'll either have no solution or infinitely many solutions. Those are the phrases, by the way. What's the difference between no solution and infinitely many? What's different about them?
Y-intercept.
The y-intercept. Infinitely many solutions has the same slope and the same y-intercept. No solution has the same slope and different y-intercepts. Okay, so today you're going to be asked to solve. One option for solving is to solve by graphing. But I'll be honest with you, it's the lesser of the options, but it is an important place to start. Now, if I want a graph to solve, then I need to create a coordinate grid. I also want to try to make each of my ticks that represent my actual grid itself, try to make them evenly spaced. It doesn't have to be perfect, because there's one other thing that I use to my advantage with that. Now, if you want a graph, y'all have done this before. You've started this in like 7th grade. You can make a table, but there's an easier way to do it when it's linear and in slope-intercept form. It's called slope-intercept form for a reason. It gives you the slope, it gives you the y-intercept. You should already know where these graphs cross the y-axis. Where does the top one hit the y-axis? At -1, specifically the coordinate point 0, -1, if that helps. So I'm going to start with the y-intercept, and then you move with the slope. The slope on the top one is that -1/4. Now generally when you have a negative in front of that slope, that negative goes on the top to try and kind of tell you movement. So it's -1/4. Is slope run over rise or rise over run? Rise over run. That's the rise. That's the run. What directions do you rise? Up and down. If it's negative, you're rising downward. So we're going to go down 1 and we're going to run 4. You go horizontally for specific, you're going to go to the right. So from the y-intercept, down 1, to the right 4. Now, when you're doing a system of equations, your best bet when you are doing that is to do that as many times as it takes for you to get all the way across the graph. In the past, when you're just drawing a singular equation, you do that once and then you connect them with a straight line and you're golden. When you're doing a system where you actually have to see where two graphs intersect, you want it to be as accurate as possible. Which means I recommend making points as far across the graph as you can get them. Can I move down 1 into the right 4 again and still fit on the graph? No. But can I move the other direction? Yes. When moving the opposite direction, make sure you go opposites in both. Instead of down 1 and right 4, I'm going to go up 1 and left 4. From here to here, that brings me back here. Up 1, left 4. Brings me there. And then I connect with the straight line because I can't go any further. By doing this, it takes care of the fact that sometimes I might not draw a perfect graph. If I've got those coordinate points drawn in, I'm more apt to be accurate. Thank you. Okay. So there's one of them. Now I need the other one. The other one had a y-intercept of +2, so 0, 2, and a slope. What's the slope on the second equation? -1. To write a whole number as a fraction, you put it over 1. -1 over 1. Rise -1, run +1. So from that point, from that y-intercept, down 1, right 1. Again, do it as many points as it takes you to get across the graph. Or if you intersect the other graph in the meantime, you're good. Down 1, right 1. Down 1, right 1. Down 1, right 1. I've intersected the other graph. I'm going to call it good enough. What's the coordinate point? Make sure you're doing left and right first, up and down second for coordinate points. It is 4, -2. Graph and look a little familiar? I hope. Okay, I've got just one more equation for graphing. And I actually don't need that much room for this one. So I'm just going to do it over here. I got the room. Reason I don't need a whole lot of room on this one is because I'm specifically deciding this one to do something. When you are being asked to solve a system of equations by graphing, you can save yourself a heck of a lot of work if you keep an eye on the slope and the y-intercept. Specifically, those no solution versus infinitely many solution options. What do you notice about the slope of these ones? It's the same, which means these lines are either the same or they're parallel. Are they the same line or are they parallel lines? Parallel because the y-intercepts are different. Same slope, different y-intercept means what's my answer? No solution. If you notice that, skip the graphing. Tell me the answer. If you don't notice that, then you should see it after you graph. The other thing you're going to see today is solving a system algebraically. Specifically, today we're going to focus in on what's known as substitution. Downside of solving by graphing. One, your graphs have to be perfect. The bigger issue, though, is if they don't intersect at integer answers, you have to estimate on it if it's a 0.5 or maybe it's a 0.3 or maybe it's a 0.7. Who knows? So there's definite downsides to graphing. Graphing is fantastic when both the x and the y are whole numbers. Not so much otherwise. So that's when we come up with different forms of solving. Specifically, substitution and elimination are your options. Today we're focusing in on substitution. Again, you've done this before. In fact, substitution, that word should be very familiar to you if you were in geometry last year or this year. Do y'all remember talking about doing in proofs, doing substitution all the time? Do you remember what substitution actually means? Not exactly. What's it mean if you have a substitute teacher? You've got a replacement in here. It means I'm not here. There's a replacement here. To substitute is to replace something specifically with what it's equal to. You can't replace numbers with what they're equal to because numbers are equal to numbers. 5 does not get replaced by anything but 5. But variables can be replaced if you know what they're equal to. Do I know what either of the equations is equal to in this setup? Yeah, I know what the y is equal to. So in the other equation, I can substitute what y is equal to into here. I can replace this y with that. Now when I do it, I have to be careful. If anything was happening to this y where I'm replacing it, I need to make sure that I'm actually taking care of that. So when you do substitution, you typically plug it in parentheses. I'm going to change this equation into 2x plus, here's where the y is that I'm replacing out, so parentheses, 2x plus 4 equal to 8. Now I'm going to have a single variable in that equation. I've just got x's. It's in multiple places, but it's still only x. And now it's just a matter of solving this. In this case, did those parentheses actually do anything for us? No. If there was a number in front, I'd have to distribute. If this was a minus, I would have to distribute. In this case, it didn't do anything. How do I solve 2x plus 2x plus 4 is equal to 8?
Putting the like terms together.
Simplify by combining my like terms. 2x plus 2x is 4x. Subtract this 4. 4x is equal to 4. Divide by 4. X is equal to 1. The solution to a system of equations is a coordinate point. A coordinate point requires both an x value and a y value. I have the x. How can I find the y? Put the x back into one of the originals. Substitute it back. The first one's going to be easier because y is already alone. Y equals 2 times 1 plus 4. 2 plus 4, 6. Coordinate points, do they go x, y, or y, x? X, y, 1, 6. This should also look familiar. Got a few more examples, but otherwise it's doing the same stuff. X equals 8y, and x equals 8y minus 3. If I want to do substitution, I need to know what one of the variables is equal to. Do I know that currently? I currently have x equals, so I know what x is equal to. Not as a number, but I know what it's equal to as an expression. So what it is equal to, in this case, 8y, can replace the x in the other equation. Can go here. 8y equals 8y minus 3. Now, some of y'all might have noticed an issue from the very beginning on this one. If I want to solve this, I want to get my y's together, subtract ay. They cancel out over here, leaving me with 0 equal to negative 3. When is 0 equal to negative 3? Never. It's a no solution. You get a situation where a number is equal to a different number, no variables involved, you got a problem. If you prefer to use the no solution symbol, that works too. X minus 3y is equal to 4, and 4y minus 3x is equal to 18. Again, if I want to do substitution, I need to know what one of the variables is equal to. In other words, I need one of the variables alone and equal to everything else. Do I currently have that? No. Which variable looks easiest to get alone is the next question. In this case, x on the first equation, because it's got a coefficient of 1. It saves us the most work. To get the y alone on the first equation, I'd have to divide by a negative 3. I would end up with fractions. To divide, here I'd divide by 4. I'd end up with fractions, or decimals would be okay. I can write them without rounding. To get that x alone, I'd have to divide by 3. So, sometimes you might have to manipulate a little bit. X minus 3y is equal to 4. To get the x by itself, to undo the subtracting of 3y, add 3y. X equals 4 plus 3y. If you prefer 3y plus 4, it's the same thing. Now I know what x is equal to. One of the biggest mistakes that I see when people do this is they accidentally plug it back into the original equation that they manipulated. You cannot plug this back into the first equation, because the first equation is what got us this. You have to plug it in here. Four y minus 3, here's where the x is, here's where I replace, in parentheses. Another very common error just comes in solving. I see parentheses with a number in front, I better distribute it. What number am I actually multiplying through though? Negative 3. Keep an eye on positives and negatives. 4y minus negative 3 times 4 is 12. Negative 3 times times positive 3y is negative 9y equal to 18. From here, y'all know how to solve, but keep an eye on when you're doing opposite operations or not. Some of y'all on the last quiz had things on the same side of the equal sign and did opposite operations. 4y minus 9y, they're on the same side, so you do what they say. Negative 5y minus 12 is equal to 18. Add the 12, negative 5y is equal to 30, divide by negative 5, y is negative 6. Once it became a basic equation, y'all know what to do. It's combining like terms, at times you screw up. Is having y alone enough? I also need x. I need to plug it back either into one of the originals or the manipulated original is fine too. Which one's going to be easiest? Generally the one where the variable's alone, the manipulated original in this case. X equals 4 plus 3 times negative 6. And we get negative 14. Keep an eye on the coordinate points. Make sure you put the x before the y. I'm going to be done there with examples. I just want to make one more quick note of something to look out for. But otherwise, I've taught you anything. So, algebraically, we saw some single solutions. We saw a no solution. We didn't see an infinitely many solutions. On a graph, infinitely many solutions looks like two overlapping graphs. Algebraically, infinitely many solutions will be a number equal to itself. Something like 5 equals 5. The variables disappear just like in no solutions. The only difference is no solution is a number equal to a different number, and infinitely many solutions is a number equal to itself. It's something that always works out. 5 is always equal to 5.